1 second. I just realized I'm on the wrong screen. Whoops. Okay, I think it's working. Hold up. Hold up. Oh my gosh, sir, it's all beeping at me. All right. Okay, 1 second. Oh, I should probably turn that mouse on. That would probably help. And then... Okay, that's working. Okay. Let us see. Yeah, so I might need to install some stuff. So bear with me. Let me see if I have it. That is not what I wanted to type in. Okay. Yeah, so I think this only installs per user, so I need to go and download this. At least this website, this program I'm going to be using allows for like a Windows installer now, so that makes things easier. But of course, when we do it, Windows is gonna freak out and be like, "Oh my gosh, this program, it's a virus." It's not. It's not. It just doesn't have it doesn't have like certificates unless they, oh, it's not? I guess they have certificates now. Oh. Hello. This is new. I guess they've done updates to this program since I last used it. So yeah, no, it just fully installs as a program now. Nice. Very nice. Well, let's see if it breaks. Because I am... Okay, yeah. Oh, shoot. Yeah, no, they just... This year released a new version. 22.01 release. Oh, I should probably move this up here so you guys can see it. I can't read that. 1 second. Display settings. Display 2. 125. Okay, I think that works now. Yes. Okay, new features. Rocket design features, pods and strap-on boosters, tail cones, freeform fins on nose cones and transitions, highly configurable rail buttons, massive update to parachute configuration and part library, Dave Cook's extensive component library now built in, coefficient of drag override for components and assemblies, and more flexible override settings in general. Oh, okay, so like, instead of using like a simulation, like if you have wind tunnel data, then you can like use that. Yeah, you used to have to use this like jar file to make this work. Okay. Well, I'm glad this is looking more legit than it used to. Okay, there we go. So, I might need to double check which motor I have. I don't have any motor mounts. So we'll start with the motor. Engine block, sustainer, body tube. Oh, okay. Oh, there's another thing that came up. Holy crap. Whoa. This is insane. Yeah, this did not have this library before. Dang. This is like all the off-the-shelf parts that you can get. Interesting. Well, we're not using off-the-shelf parts, so we're good. Body tube custom. We could use the parts library. This component is a motor mount. Ignition at launch. Okay. Now let's get a motor. Oh, whoops. And new configuration. Let's see. So it's filter motors, clear all. I'm using an Estes motor. I believe it is a C6. Okay. Body tube. Edit this. General. Yeah, 1 second. Let me go look up which motor I have really quick. Okay, yeah, they are C6 motors. And then let's look up really quick the dimensions. Okay, let's see. What technical specifications? They're 1.3 pounds. They're 18 millimeters in diameter and 7 centimeters in length. Oh, 18 millimeters, not centimeters. I was going to say that doesn't sound right. Inner diameter is in centimeters, 1.8. Design centimeters. Well, thickness. .8, whatever. Half a centimeter. No, inner diameter is not 5 centimeters, is 1.8 centimeters. Length is 7 centimeters. And then actually the motor should probably stick out a little bit, to be honest. Do 1 centimeter overhang. Make this 6 centimeters. Or 7, either one. Outer diameter 5 centimeters. And we can... Let's make this 3 centimeters for now. And this will be plastic. Blue tube? No idea what that is. Cork. Cork is a really good rocket material. I have cork in a bunch of stuff. Cork is great for, like, fire stuff. It does not burn. Well, it does. It just burns incredibly slow. I think I'm going to be doing it out of PLA, so 1 second. What's the approximate density of PLA? About 1.25 grams per centimeter. Custom. Oh. PLA 1.25. That's if we're doing solid. Add material to database. Boom. Now, this doesn't help us go as high as you would necessarily want. However, it does help. Okay. Now we're going to do body tube. I should rename this one. Edit, rename. This is the motor mount. Okay. Put this up here. I forgot. There's a way to... Oh, inner tube. Ah, got it. Okay. A second. I might delete this. Make this that. Inner tube, inner diameter 1.8, length 7. That's exactly what we want. Motor. This component is a motor mount. Okay. Let's delete this. Motors configurations. Inner tube. And we're going to select a motor. We're going to use our C6. Okay, we have a motor, it's loaded. Edit this. Motor mount 1. It's because this is our stage 1. If we wanted to go higher, we would use multiple stages. Let us see. That would be fun, but I need to... The issue is that I need to do some other stuff. Okay. So I don't want to put too much weight back here in the back because it hurts our static stability. I think we're going to try to shoot for a static stability of about 1.5. That's usually good. You want somewhere between 1 and 2, usually. It's more of like a rule of thumb rather than a hard rule. But for a static where we're not actuating any control surfaces to like correct stuff, static stability is kind of what we want to focus on. Edit general outer diameter 1.9. We'll make that 3. Okay. Then body tube. Then a nose cone. Do an ellipsoid. One second. There we go. And then pods. Oh, those are new. Yeah, and then we'll do some elliptical fins, because those are really easy to print. Body 2, elliptical fins. We'll do 4. Yeah, so there are a couple things we can do. So you can see this is a general setup for a basic rocket. And you can see here that we have a couple different things set up right now. So we have the big thing is what makes us go fast and high. We have a rocket motor, and that has a certain amount of weight, and it's made with gunpowder. And as we burn that, we basically generate up force that will fling us forward. As we're flying up through the sky, this red dot is more or less where all the aerodynamic forces, you can kind of imagine them all working as like one arrow through here. That's not what actually is happening, but it's an approximation to make things easier to visualize and design. And then up here, this little fun doohickey is our center of gravity. So there are a couple different things that affect how high we go up. The biggest one is going to be how much drag we incur. So there are two ways to increase sort of our... Well, there are two things. They're drag and then our weight. So those are the two things that we can do, that we can fiddle with to affect how high up we're going to go. But the easiest one the one that will have the most effect is the drag. Because the faster you go, drag is proportional to how fast you are going squared. Whereas the weight is only proportional to how heavy your vehicle is, which reduces as the motor burns up. So those are the two things we can do to affect how high we want to go. And we don't want to go above this apogee, 100 meters. We don't want to go above 400 feet due to legal reasons where we're going to be launching. And it's just not, like, it's better when you're first starting out to start low. So, let's see. 400 feet in meters is like 120-ish? Yeah, 121. So we don't want... This is all in metric, so we'll just work in metric for now because it's easier in this design software. This is a bullet? Yeah. Welcome on in, Sam. This is not a bullet. It is... a bullet doesn't carry its own fuel. How was my Sunday? I woke up late. I meant to go somewhere today and I didn't. But I want to get something in so I feel like I've accomplished something before I go to sleep. So yeah. So let's see. Apogee 136. I'd put like a big 50% margin of safety on all this, so 50%, we could probably do 25%. So 120 times 0.75 is 90. So let's aim to be below 90 meters of apogee. Yeah, it's a rocket. They made some nice changes to OpenRocket. It's nice. Okay. So, and it has the same impulse, so it should be a good approximation for the rocket variant that I have, or the engine variant that I have. So I'd say we go for the weight, and then we also want the stability to be around 1.5. So One way we can, the best way to reduce how high we're going is to make the rocket fatter. And the best way to increase this is to make the rocket longer. Or and make the rocket longer and make these fins larger. So the larger these fins are, the more correcting force they make when the rocket tilts. So let's go to the body tube, edit this. Actually, let's go for the stability first because that's really far out of spec. So let's do stability first. Okay, and then honestly, if I could, I would not make this more than 20 centimeters. Just because of manufacturing reasons. Oh, I'm making it go up. Let's try 20. And then we will make this big and chunky. Okay, and then we'll work with the fins. Speaking of, Sam, how was your Sunday? 0.3 centimeters. Maybe 30 millimeters. That'd be good. And a fin cross-section square. That's the easiest. Should set that for all. There we go. Ooh, that like really messed stuff up. Of course it did, because it threw off the it threw off everything. Wall thickness of 0.2 centimeters. So 2 millimeters. Here's a trick. We can make the cone thicker. Yeah, if we make the cone heavier, it will increase our stability. Because we're moving, the stability is a measure of the distance between this point and this point. We want, for a stable front flying rocket, we want the weight to be up towards the front, and we want the aerodynamic center to be back here, mostly near the fins. And we want the distance between here and here to be about 1 to 2 body diameters. That is a good rule of thumb for having static stability. If you don't, then it if you do it too much, then it overcorrects, and it like, as it's going up, it does kind of a this motion. If you don't do it enough, then your rocket tumbles as it goes up, which is no bueno. And you can fly rockets that are statically unstable as long as you have an active control system that is fast enough to compensate for that. But we're going low tech first. It's good to start low tech and then work your way up. Okay. We can always make these bigger. That's really easy. Bottom of the parent control. And can't. Oh no, we don't want canting. Canting doesn't really do you much until you're going fast, and by the time you're going fast, you're going fast enough that it's better just to have bigger wings. Okay, we're not getting... We start getting diminishing returns after 7. So I'd say 7 centimeters is probably our go-to. And then we can increase the length. Oh yeah, and our apogee is well within what we want it to be. Perfect. And then let's... This was 20. How long is this? Because we can have this be up to 20 as well. 20, and we're about... Oh, did I beat a metal? I did. It was a fun game. I really enjoyed it. It was a silly game, but it was a fun game. Let's make this be 0.6. Oh, wait. There we go. Now we are beating our stability, our stability goal, but not by too much. And we're beating this too. And then we need to, just to make sure, I'm going to throw in rings in here. A rail button. We'll put in an engine block. Actually, let's put the engine block in here. That would make more sense. Close. Engine block. Top of the parent component. PLA. Okay. Yeah, no, I did beat a metal. It was a lot of fun. And I think if... Cancel... I guess we put it in this body tube. Centering ring. Perfect. Righteous Arsonist. Well, come on in. Who is your favorite schizophrenic programmer? Honestly, I don't know. I don't, like, I do programming, but I don't, like, I do it as part of my job. So I don't, like, I'm very basic in my programming. But yeah, welcome on in, Arsonist. So, since it's your first time chatting, my name is Aixer. I'm a full-time aerospace engineer and a part-time VTuber. So what we're doing today is we're kind of going through the basic, like, sizing of a model rocket that I'm making using 3D printing. So everything here is going to be made out of plastic parts, and the reason why is because I am terrible with my hands, and 3D printing and making machines make stuff for me is easy. And since I'm not trying to get as far, as high up as I absolutely need to, it's totally okay. Terry A. Davis is my favorite schizo. What kind of fuel does it use? This one uses, we're using an Estes gunpowder rocket. So it's a gunpowder solid rocket. and they're way overpowered for what I need them to be doing. So I'm trying to get this to be below 90 meters for safety reasons. And we're doing pretty good right now. So we're at 50. I don't want this to go super high. I have a million of these motors. And the next time I buy them, I'm going to be buying weaker motors. But I have way too many of these, and I need to get rid of them. Do another centering ring. Ooh, do. PLA. Okay. Okay, so it did, like you see, we are adding weight back here, but you can see our stability is smack dab in the middle of 1 and 2 calibers. So that's what we do. What use can you possibly have for a low-powered rocket? For funsies. So this is more of me exercising my design skills. So there are a lot of times. So the reason I'm doing a low-powered rocket is because it allows me to be able to fly it in more zones. So if you're anywhere nearby any airport anywhere, you have to be a certain distance away from the airport in the US, and you also can't in general, you shouldn't be flying above 400 feet. So this one has an apogee of about 50 meters, which is still pretty high for the human eye. And that should be about 164 feet in the air. So we're still going pretty high. But again, especially when you're doing a first iteration of something, you should always start low and work your way up. So that I guess that to answer your question, we have certain restrictions that are put on us. So we're designing within those restrictions. Yeah, so we have certain legal restrictions, and we're trying to fit those. Can I have any payloads? So this is going to have a payload, but the payload is going to be a flight computer that tracks how high I'm going and tracks the acceleration through the entire trip. Any payload we put up here will increase the stability. But yeah, when you do this, you do want to add in a payload. But we're just doing the basic sizing for now. We will, since we're probably not going to be changing anything outside here, our center of pressure is probably a very good approximation. But before we fire, once we put everything together, we're going to want to physically weigh where the center of gravity is when the rocket's all loaded up, so we can double check the stability number. But yeah, so generally these things are designed. So these SC's rockets, they will burn, and then they have a charge that fires out the front. And so what that does is that detaches the nose cone, so you can deploy a parachute. Because if something goes up on Earth, it generally comes down. And we don't want heavy plastic things falling from the sky on top of children. Or people, or anything in that matter. So that's why we use parachutes. Let me just throw in... How heavy is this? It's going to be about between 200 and 800 grams. Let me see how big of a parachute I should have. Is it accurate enough for precision strikes? No, unfortunately it is not. However, I have done I have tried aiming them before for when I was in school. That was one of our projects. We needed to hit a certain altitude within a certain time frame. And that was fun. But was it precision? Absolutely not. So this is statically, the fins are our stability thing, and our fins do not move. If you want anything that's precision, you need control surfaces that can move and compensate for changes that you can't calculate for upfront. And that's a whole nother engineering. It's called control systems, and it uses a lot of what are called Laplace transformations. So if you've ever done calculus or differential equations, towards the end, usually they teach you a little bit about Laplace transforms. Let's see. Can it be done with an Arduino? Yeah, absolutely can. The only thing is, if you do an Arduino, I do believe you need to up the baud rate. Because you, depending on how fast you're going, you need to make very fast, small corrections. And if you ask, can you use GPS? Technically, yes. However, unless you are working outside of ITAR, which is the International Trade in Arms Regulations, for any useful precision strikes, a GPS would have to be hacked in order to function at the speeds that you need for a precision hit payload deliverer. So I if that's your question, sorry, unless you're willing to majorly break international law, that's not going to happen. Parachute design. Use of a spill hole. Okay, so parachute size. As a general rule of thumb, the design for this parachute descent velocity of your rocket is 3 to 4 meters per second. You can determine the area of your parachute from the following equation. Oh, okay, yeah. No, that makes sense. That's an equation area for round parachutes. Let's just use that one because that's easier. Let's just do a quick one. Okay, I'm gonna want like a 27 to 23 inch parachute. And one second. And can the fuel be repurposed as a payload? It depends what kind of payload you want. I don't care about the law. So I hope you're doing a bit because if you're not, I can answer questions that are like publicly available, but like if this isn't a bit, then I am morally obligated to not answer. But if it is a bit, then it's totally okay. I just have to I have to make sure. Parts library. I could just get an Estes rocket. 24. We'll do this one. Diameter, top of the component, packed length, packed diameter, shroud lines, top. Okay, we'll put the parachute there. And then I think it's like 3 grams. And the nose cone for the computer. We'll put that up here. Okay. Bada bing, bada boom. There we go. All right. So I think that is a good first first rocket. It does look like our apogee has dropped significantly, so we can probably tighten this up. So we're well inside of our what we want to do. So let us narrow this up, and then we can shorten a little bit. Let's do 4 centimeters outer diameter. Okay. Nose cone. Oh. No, these are all supposed to be PLA. Why are you changing yourself? Set for all. Okay. Yeah. Okay, and then this nose cone. Base diameter is 4. Okay, we have way too much stability. So let us... Let us shrink this. Okay. And then... Usually you put the parachute in the tube, but I'm going to put it in here. Actually, putting it in the tube is probably a better idea. Yeah, no, actually putting it in the tube is a better idea. Because then it will actually launch it out and deploy it. But we will put it at the top of the tube. And then we can... Let's shrink this body tube a little bit. To 18 centimeters. And then we can decrease our fin by like a centimeter. Okay. Okay, I think we're doing a little bit better. We can go a little bit higher. Staying within, well below any... We're staying well inside of the non-compressible zone for approximation, so that's good. Max acceleration. Okay. Honestly... See, how big is this tube? Because it's 1.8. centimeters. We could make this real simple. If we just basically shrank this to the size of the tube. So let's see. I think we have plenty of wiggle room here, because we're only doing a third of our limit on Apogee. So let's shrink this up. Edit. I guess it's not doing automatic for some reason. We'll do 3 centimeters. Yeah, we're up to 50. .8 plus 2. I want a wall thickness of at least 5 millimeters. Well, the easiest would be to do, if I do 0.4 to 0.7, I think I can do 0.8. Let's try 0.8 millimeters. If I use a large diameter extrusion nozzle, then I might be able to get away with it if we do it in vase mode. Let's see. The nose cone, we don't have to, but the body tube I would like. Wall thickness, 0.2 millimeters, 0.8. So wall thickness is 0.8. That's outer diameter of 2 centimeters. Okay. And we'll put centering rings, the motor mount. Oh, sorry, that's the engine block motor mount. Okay. And then we will, on the fins, let us bring them down in height. Okay, let's keep them up in height. We can reduce our stability by making them bigger. There we go. No, not cardboard. PLA. Let me make sure everything is PLA. No, why is it? I feel like it's all trying to make itself cardboard again. Edit. No. PLA. Okay. Edit. PLA. Okay. Okay. And then elliptical fin set. Putting it right at the bottom. Fin rotation. Fin cant height. Root chord of 7. We could do 6.5. There we go. Okay, so we're within 10 meters of our goal, of our limit height that we want to reach. Our stability is good. Mass with no motors. Mass. Oh shoot. We do need to change the. We need to change the parachute. So we're about half of what we wanted before. So of the weight. So let us. This is kind of how stuff goes. Is as you change stuff around, you get different. You have to change parts around as you change the mass a lot. Change. We'll do the STs. We'll do the 18. Close. Okay. All right, that's still a little oversized, I think, for what we need, but that should be good. Actually, I am going to go even one further down, because you do need to be careful with getting parachutes that are too big. If you do a parachute that's too big, that's also not great. Parts library. Estes 12. I don't want to do quite 12. We'll do an 18 and we'll cut a hole in it. Okay. And then we'll do a flight simulation. And simulation. Velocity at deployment. That doesn't make sense. New simulation. Simulation 2. Average wind speed, that'll be good. Average deviation. Turbulence medium. Wind direction 90 degrees. Always launch directly upwind or downwind. Length of 1 meter, which is kind of what I want to do for the launch rod. Latitude. Simulate and plot. Plot. Okay, let's see. Vertical velocity. That's a 10. That's a 4. I think, yeah, so going down, we launch up. Hello? Why is my battery not? Why are you not charging? 1 second. Someone may have unplugged things in my set. Okay, apparently we're just not charging. Wonderful. Okay, well, I think we're going to save this for now. Save. And this is going to be Clover MK1. I'm going to save that. Rocket design. Save. Okay. So now we're good, even if computer decides to stop charging. Yep, we're not charging, so. All right, then. So we have our base design. I'm going to go take this. I'm going to go put it somewhere else to charge. No, because everything else that's plugged in here is charging, so maybe the cord just isn't working. Oh, I see. I think I see now. Let's try this one more time. Oh my gosh. My charging brick, the plug had backed out. From the wall to the other thing. So we can keep going. I say that we could keep going, or I think what I'll do is I will save this for another time. I am interested about that person that Arsonist brought up. Who's Terry Davis? Design Temple OS, a public domain operating system. It's the almost. He learned assembly language, electrical engineering from Arizona State. He worked at Ticketmaster. And then he actually has bipolar disorder and schizophrenia. Okay, I was wondering if the Temple OS was religious in nature. Yeah, he's trying to make another temple, which after Herod's temple. Holy crap. He got hit by a train at 48 and died. Holy crap. I feel sorry for this guy. I feel sorry for this guy because, like, schizophrenia is crazy. Like, you think everybody's out to get you. Whether or not that's true is something else entirely, but like that's rough. Okay. So I think we're good. Yeah, so everything, we're basically fitting this rocket. One second. Maybe I can plug it back in now. Now that my computer is actually charging. Yeah. So we've done basically what we were supposed to do with rocket design is our payload, you design around your payload. Our payload is the rocket itself, essentially. So we don't really care about anything else. So that simplified things for us. In which case, we selected a propulsion system, which is this rocket motor right here. And we basically just formed it as much as we could around this, while keeping certain manufacturing needs in mind. For example, this part right here, this is going to be basically a tube. We're probably going to put tape on the inside to keep the layers together, made of PLA. And then this rocket up here is not going to be, and this is going to be done in vase mode. And this one up here, we can probably print with thicker layers. It'll take longer. It won't be air quotes as strong, but it will have more layers, so it should generally have better adhesion. We'll put our little flight computer up here. It'll have a little port going to the outside so that it can get pressure data. We have our wings, which look kind of like a clover. And then there's another way for me to do this. 3D figure. Yeah. So yeah, so it looks kind of like this. And because of the elliptical fins, which are hard to do, and most people don't bother, but because of this is why it's called the clover. It's because it looks like a clover. All right. So yeah, I think we've done good there. Let's save this one more time. But yeah, from what I seen, the simulation is good. So the next part of this would be to build to this specification. So we're going to try and get this as close, build a rocket as close to this as we can get. And then we will verify the design by shooting it off. And I may or may not film that. I don't really have any good video filming cameras, but we'll see. But yeah, no, I'm happy with this. This is pretty nice. So. But yeah. So I think I'm gonna wrap up for now. Sorry if you're just coming in, but I'm gonna wrap up for now. But I think I'm going to play a game tomorrow, and then the day after, I think I will go on the 3D CAD design of this version. So basically designing like the actual production model. And then we'll 3D print the parts and make them so they fit together and stuff. And that'll be fun. All right. Let's see. You know what? Since I'm ending early, there are people that are still on. So let's go raid. Let's go raid somebody, actually. Oh, yeah, 1 second, wrong computer. Let's go raid Soy Milk. Have I sent you guys over to Soy Milk before? I don't think so. I think... How long? She's been doing for 3 hours. I think she usually does more, so let's do this. Yeah, so Soy Milk is you're unsure? Yeah, so Soy Milk is also somebody that does science and stuff, but on the VTuber side, she does VTuber rigging. And right now she is doing Amazon product reviews. And from what I've seen, they're hilarious. So I'm going to send you over to her. But yeah, she just recently graduated with a degree in computer science. So yeah, let us see. /raid soy milk. She's really funny. So once again, be nice. Let's get a raid message going. We'll just do well, now I'm gonna be mean. Excellent. This will be our raid message. But yeah. So yeah, be nice to her. She's really cool. And she's also really funny. So feel free to poke fun a little bit. Her streams are kind of okay with that. So but yeah, and if you have any really cursed Amazon products, if you go into her Discord, you can put them in. I think the mods are sending them over to her. But yeah, no, thank you everybody. I've seen some cursed stuff. Yeah, just as long as it's stream appropriate, as long as it's TOS. But yeah, as long as it's in TOS, cursed stuff, totally awesome. So I'll send you guys over. And thank you guys so much for coming over and hanging out. I'll see you guys later. Bye.